Hello, everyone. Thank you for being here for our new meetup on gas consumption forecasts. I'm Natalie. I'm the marketing manager at DC Brain, and I organized this event. So I'm very happy that we're almost 40 now. We're almost 40 people connected. I'm very happy you're all here. Before we start, I would like to show you the Livestream platform. I don't know if many people have used it before. So just let me share some of the functionalities. So you see here, there's a chat function where you can say hi, and some started saying hi already, so that's great. So you can say hi in the chat function. You have questions also. If you have questions during the conference, then you can ask them here. A nice feature is that you can upvote questions, meaning that if there is a question which you find very interesting or which you would like to know more about, you can upload it. And we will see it and we will answer every question that comes up. And we have the polls here, and we will have the opportunity to post one or two polls during our speakers' interventions. So let me introduce you to the speakers. Then we have Nicolas Jensen, who is a senior policy advisor at Eurogas, a gas association, European Gas Association, representing the different gas sectors. We have Antoine Mazy, who is head of energy logistics at Gazak. Gazak is the main natural gas and electricity vendor in Berlin. We have Maël Capino, who is our data scientist, and he specializes in gas, so you can ask him any complicated question, technical question. And we have Arnaud de Moissac, who is our CEO, and who will conclude the conference. So you can ask him questions at the end too. And just one sentence about DC Brain. We're an AI startup, and we're specialized in gas networks. And we tackle complex optimization issues in complex gas networks. So Maël will tell you more about this. And I see we're more than 50 people now. So just before we start, let me remind you that you will all have access to the replay. And I will send you an email with the resources, meaning the presentations of all our speakers by tomorrow. Right. I'm handing over to Nicolas. I will just share the presentation. And there you go, Nicolas. Thank you.
Fantastic. Thanks a lot, Natalie. I think so. You will be the one changing the slides, right?
Well,
I don't have direct control. Perfect.
Yeah.
Great. Thanks a lot for the kind introduction and for the kind invitation, Natalie and DC Brain. I'm very happy to be here with you today to discuss this. As you said in your introduction, complex optimization in complex gas networks is something that is becoming increasingly important in our day and age. What I'll try to do from my humble public affairs background and non-engineering, non-PhD, is to try and set the scene a little bit for what is happening in Europe, what kind of trends we're looking at, and why it's exceptionally important to look at those questions today and in the years to come. So diving straight into it, just very briefly building on what Natalie has said, in Eurogas we're representing 53 association and companies from the gas sectors. We're looking at certain parts of the value chain, so we represent wholesale and retail actors, so the market part, and we also have distribution members, so distribution system operators, and basically the last mile in terms of pipeline that brings the gas within the cities and to final consumers. Why are the questions of forecasting and new gases especially important in that respect is, as we've already had some large evolutions over time, whether we're looking at going from town gas to natural gas, and in large areas going from H gas, L gas to a single type of gas, we're now looking at something even broader with various types of gases. So what I want to do today is try and unpack a little bit the comprehensive title for the session and look at the various parts that are made up of this. Within Eurogas, I focus on distribution networks. I also focus on everything related to methane emissions and sustainable finance, as well as renewable and decarbonized gas development. So if there's any questions on that, I'm happy to answer them. And I think you'll probably find that a lot of those topics come together when we're looking at forecasting and the next couple of years and decades, to say it quite directly. So the first part of what we have to look at when we look at forecasting is how do we deal with the old and the new in terms of regulation. What we're looking at today, of course, is an energy system which is Paris compatible, which is decarbonized and climate neutral by 2050. We're looking at very large scale and comprehensive decarbonization within the Green Deal, because we're looking at climate neutrality across sectors. What does that mean? It means that certain sectors might continue to emit a little bit, certain sectors might be climate or carbon negative, and overall that has to kind of ease out across sectors to make sure that we reach climate neutrality and are Paris compatible in the approach. What does that also mean? That means that looking at the energy system today and the way that we consume energy, we have to try and emit less, both with existing infrastructure, but also by building new infrastructure that might be necessary in the energy transition. And I think here is the first part where the optimization comes into mind, and we really have to put it at the center of the discussion. The second aspect, which I think is important, and I hope will come up in the discussions and the questions later on today, is increasingly policymakers and consumers want energy to be traceable, and particularly renewable and decarbonized energy to be traceable. What does that mean? It means that if you purchase renewable or decarbonized energy, you want to make sure that what you're purchasing is indeed renewable, is indeed green, and does help the energy transition. So it is the actual product that you wanted to purchase, which is delivered to you. How does that work in a system that is, of course, completely interconnected? And considering we're working with an internal energy market where, to a large extent, you have to be able to buy energy from other countries, how do we make sure that is traceable? The first element to have in mind is guarantees of origin. So how do we make sure that certification works and that traceability for molecules work? I think that's quite a big aspect of what we're trying to do or trying to look at in terms of network optimization as well. Mass balancing. What does that mean is within a single energy or single logistical system, everything that is injected somewhere is consumed somewhere else. So how do we make sure that overall this works and that the planning and distribution system operators or transmission system operators can work with this? How do we contend with direct connections or not? A lot of the existing legislation is trying to look at renewable energy that has to be consumed directly and can't travel. So how do you optimize your network in that sense? And how do you make sure that consumers can access what they're looking for? And finally, how can buildings actually consume energy which is not produced on site? How do we use all of those various parts of the puzzle to create a single system that can help end users consume renewable energy? The final point here, before moving on, is that we're changing paradigm completely, because we're moving away from a system that has always been more centralized. We import gas, we import energy, or it's produced in large assets that are very localized, to a system where, whether on the power side or the gas side, we increasingly produce in a decentralized way. Looking at biomethane production units, looking at electrolyzers in the future, the flows will be completely changed. So it will no longer be a system where you're looking at large external production going from TSO to DSO. You will be looking at energy also flowing from DSO to TSO and in reverse directions. What does that mean? That means that existing legislation may need to be adapted, and existing standards may have to be adapted to make sure that the system is ready for the next steps. What are we looking at in terms of new gases when we talk about this kind of need for increasing planning and the increasing complexity of the system? We're looking at new gases. What do we mean by new gases? We mean gases that may have been in use before, or in terms of town gas historically, there was very high blends of hydrogen with methane. So it's not something that is fundamentally new, but it's a shift. It's a shift from exclusive methane networks to networks that may either be blended with hydrogen and methane, or 100% hydrogen networks. Now, when we look at new gases, there are two aspects. There's the technical and the market aspect. The technical aspect is quite simple. What are you looking at in terms of molecule? Are you looking at hydrogen, or are you looking at methane? And the second aspect, which is less linked to the security or the technical feasibility of the grid, but is more linked to end users being able to access the gas that they wish to consume, is linked to how you label or how you certify your gas. What is on this slide, and I don't want to go into too much detail, is a proposal that was made by industry a few years ago to better label various types of gases depending on the way they are produced. So here you have three categories, or four if you count the traditional natural gas category. You have a renewable gas category, which is defined in European legislation, where you can see that you have a mix of decentralized production units. If you look at the processes, so anaerobic digestion, very much decentralized, pyrolysis, decentralized as well, power to gas and photocatalysis would be in the same vein. And decarbonized and low carbon gases, where you might be looking at larger scale production and more in the traditional sense of centralized production versus decentralized. Why is that important? Because it feeds in the whole understanding we need of a future energy system, which will have both decentralized and centralized dynamics for gas production, and which will require the kind of planning that today might not either always be the case, or might not have been required to that extent. How can we understand that even more clearly? And I'm saying that at the same time showing it quite a complex picture that I could probably spend half an hour going over, but I want to go to the essential parts. What we're dealing with is also new constraints. If you look at this picture and you think, what is the traditional gas system? It's mainly what you see on the bottom right. So gas to power, the traditional way of feeding into the electricity system from flexible gas electricity production units, CCGTs and the like, as well as gas to heat and power, so cogeneration units. Those two ways of producing power and producing heat, let's say, are the traditional way of using gas in the energy system, or at least what we've been considering for the past decades as the core focus. What we now see is, of course, new dynamics. Power to gas, you can see on the top left, which provides new flows from electricity that's being converted to hydrogen or converted to methane. At certain times where it might be unplanned, as a way to alleviate the pressure and congestions on the power sector, or even just as market optimization. Anaerobic digestion are also new types of flows that otherwise wouldn't have had an impact on the system in the past, as you have decentralized production. And then looking at all the other stimuli, you can see external imports, LNG, liquefied hydrogen, or the production of hydrogen directly from steam methane reforming or pyrolysis, which also adds overall complexity. What is this, or what are the concepts we have mainly in this picture? It's sector coupling. Which, Antoine, working for Gazak in Germany, will be more than familiar with the famous Sektorkopplung, which is basically the whole discussion of gas and power and how they've always interacted in the past. And now the broader concept we're seeing today of sector integration, which means all of the sectors that consume, whether industry, mobility, households, power, gas, heat, all of those sectors are interacting at much faster rates than in the past and having impacts on each other throughout the days, the weeks, and the seasons, which is something we have to contend with increasingly as well. So So why should we actually care about all of this? Because in the end, of course, we have a system that's working well. Natural gas is being fed to houses, providing flexibility to the system. We have a liquid market for it. It's well interconnected throughout Europe. But this is increasingly changing, and the flows, as I mentioned, are also increasingly changing, and most likely that change will accelerate even more in the future. Some examples, but really these are only a few, even if it already looks quite like a long list. These let's say you can find new initiatives on a daily basis. But if we look at evolutions, they've been quite dramatic in the past few years. In Denmark, more than 20% of gas consumption today is already biomethane of all the gas that's consumed in the country. That's decentralized production that might have to be reversed into the transmission networks, and that provides a whole new dynamic to the system. In the UK, they want to go to 70% of hydrogen in heating by 2050 through the stepwise conversion of large consumption centers. In Ireland, industry wants to push for 20% of biomethane and gas consumption by 2030. And several studies have shown that they could go up to 50 terawatt hours, which is the whole Irish consumption. In France, as many of you will know as well, there's a large industrial roadmap that's been set for between 10 and 30% achievable by 2030 of renewable gas being consumed, and over 100% by 2050, so even potential for exports. In Sweden, most of the consumption today is biogas and biomethane in transport, and that will grow even more, so up to 15 terawatt hours by 2030, at least in national roadmaps. These initiatives are mostly industry-led or early, let's say, governmental roadmaps. If we now look at the current boom in hydrogen strategies and hydrogen development, the numbers are even more impressive. As you probably know from the hydrogen strategy that's been developed at the EU level, we're looking at 6 gigawatts of projects that have to be rolled out by 2024 and over 40 gigawatts by 2030. That's within the European Union, and an additional 40 gigawatts outside of the EU. For potential for imports. In France, the government has set forward a roadmap for between 6 and 7 gigawatts of hydrogen production, so electrolyzers and gigafactories, with 7.2 billion euros committed to it. In Germany, it's 9 billion for 5 gigawatts. In Spain, it's about 9 billion as well for 4 gigawatts. In Italy, they're looking at 5 gigawatts and 10 billions of overall investments. In Portugal, which is one of the countries more strategically involved in the topic, they're looking at about 1 billion in public funding and several gigawatts of projects. Netherlands, Austria, and Poland, even a country like Poland, who historically has been looking mostly at traditional markets, has a roadmap for 2 gigawatts development and a national hydrogen strategy. So I think it should become clear why the importance of adequate forecasting and adequate locational signals are important when planning the let's say future production centers and choosing the ideal location on one's grid where to connect these depending on the way this is optimized. And I think just in terms of closing, I'm already a little bit beyond time, so apologies, Natalie. Please cut me off if it's really getting too long. But when we're looking at next steps, and well, I would say one of the main next steps is, of course, getting the discussion going, and that's what we're doing in many different forums. We have set up what we call a prime mover group to discuss gas quality. It brings together the whole value chain from production to end users and consumers to look at how we can mitigate the impact of the changes in gas quality. So how can we best deal with increasing blends of hydrogen in the networks? How can we deal with increasing fluctuations of production throughout the year? This can put a strain on local grids. This can put a strain on end users. And overall, this can have a huge impact on the cost of the energy transition, how well we can optimize the whole way that gas quality is being dealt with. The second aspect is there's a huge revision in terms of legislation that's underway and that should be proposed by the end of this year, which is the gas package. So gas directive and gas regulation at EU level, they legislate the way that infrastructure is set up, infrastructure access, and infrastructure planning can be done. And this, as well as secondary legislation, will be very important in making sure that the system is optimized and that end users can access what they're looking for. And the third one is, of course, as we just saw, the various roadmaps that are being developed at the national level really show the direction we're going in, and why the kind of tools that can be offered through digitalization can really help whether it's distribution system operators, regulated entities, or producers, optimize the way they feed into the system and where they can locate their production units and their production assets. And looking at demonstrator units and national roadmaps will also increasingly give us the kind of feedback and experience we need from industry and from individual projects that can also show what are we missing or what do we still need in terms of digitalization and tools to help this energy transition really take shape. So I would stop here, at least in terms of the opening points. As I mentioned, very happy to answer any questions either now or towards the end. But I would pass it back to you, Natalie, and at least breathe for a second and take a gulp of water.
Thank you. Thanks a lot, Nicholas. Thank you for this very interesting overview. I know we could go on for hours because there is so much more detail that we could talk about. And so if you have any questions in the audience, then you can just write them down in the questions tab. Nicholas will be able to answer them directly, just like a chat function, basically. And yeah, thanks again. And I think we can hand over to Antoine if you're ready. Antoine, you can share your screen, or you can just click on the right hand on the right side of this presentation.
I prepared everything, so I'll try to share my screen.
Right.
Oh. So we tried it before. So I'm sorry it doesn't work. So I will, maybe you can start the presentation from your side.
Yeah, sure. Yeah, so you can start from here. You can just click on the arrows on the right-hand side just to switch pages here.
So thank you very much, Natalie, for the introduction, and thank you for having me today. It's a great opportunity for me to tell what we do at the Gazak Group and how we deal with energy forecasts. At the same time, it is quite a challenge for me because I haven't made a presentation in English for a long time in a professional context, and it is the first time on such a digital event. You may know, forecast algorithms can be very complex, as well as market rules in Germany, both at the focus of my presentation. So I did my best to prepare slides that make complex facts easy to understand. I hope I succeed in it. Before we start with the presentation, a few facts about me, so that you understand why a French guy is telling you about forecasts and market rules in Germany. I studied around the turn of the century in northern France, in Berlin, engineering studies. Then I took several positions in French and German companies in Berlin with a focus on the German energy market. I had the opportunity to work in operation, in business intelligence, and in forecast. And since last year, I am the head of energy logistics of the Gazak Group within the department Energy Procurement. My team and I are responsible for the operation of the balancing groups and for the energy forecasts. this way. Let's start with my presentation. I will first spend a few words about the Gazak group. Then I will give you an overview of the energy market design in Germany from the perspective of the balancing group manager. And finally, I will give you our recipe to get accurate forecasts. Let's start with topic 1, a short presentation of the Gazak group. Gazak is certainly one of the oldest energy suppliers in Europe. Gas supply started in Berlin in 1847. So the company is proud to say that it is 173 years old. Within all that time, it had to face with major events of the history in Berlin, expansion between the two world wars, then destruction and rebuild in the years after that. In 1985, the network converged from town gas to natural gas, an event that you mentioned, Nicola. To make it possible, the networks from East Berlin and from West Berlin had to be merged, and it was already 4 years before the fall of the wall. Now, the challenges are liberalization and energy transition in a metropolis city. So Gazak has been diversifying its activities to electricity, renewables, and energy services. Where does Gazak stand today? Gazak provides 800,000 customers with natural gas, green electricity, and energy services. We have customers all over Germany, but we focus on the metropolitan region, Berlin and Brandenburg. We record the greatest growth in electricity. We started for 5 years, and we provide our customers exclusively with green electricity. Moreover, Gazak operates the gas network in the region with its subsidiary, the Netzgesellschaft Berlin-Brandenburg. Let's go on to topic 2, market rules in Germany for third-party access. As I said, this rules are pretty complicated. At the same time, there are some similarities between gas and electricity. And for both gas and electricity, you need good forecasts. Let's have a look at that. I'm very proud of this chart because I spent a lot of time to make it. It is very a way to show how complicated it can be. To me, one of the reasons why market rules in Germany are so complicated is that there are plenty of players. In electricity, you have 4 so-called TSOs, transmission system operators. They operate the over-regional electricity network and they ensure its stability. In gas, you have 12 TSOs. Fortunately, they organized themselves into 2 market areas. In most of the case, if you procure gas only from the German markets, you do not need to book capacity on the transmission network. So we have very small capacity for the Gazak group on the transmission network. Most of the time, we deal only with the 2 market area managers. On the distribution level, you have almost 900 TSOs in electricity and 700 TSO in gas. As soon as you inject energy into the network or deliver energy to final customers, you have to deal with all these market players. This means you have to conclude standardized contracts, you have to set up electronic communication, you have to monitor this electronic communication, and you have to handle billing processes. The balancing group itself is the contractual key to access to the market. On the one side, also on the left side on this chart, you bring your energy production. As you see, we have a dedicated balancing group for renewables. It is a condition to be eligible for subventions. On the other side, we deliver energy to final customers. At Gazak, we have set also a dedicated balancing group for that. And finally, to access the exchange marketplaces, we have set up a trading balancing group over everything. I lost my presentation. Can you still see it?
I can't see it anymore. Hang on, I'll just get it back on.
Oh, great. Thank you. Our trading balancing group on the overall is connected to all other balancing groups. So it is the one that has to be balanced to 0. To buy and sell energy on the marketplaces, you also have to consider the timeline, which is specified in your contract. This timeline is the same for all market players to ensure synchronized operations. Basically, most of your deals have to be nominated on the day before. So it is based on energy forecast. Then the TSOs or the exchange places check that your deals on nomination match with your counterparties and that your balancing group are balanced. After gate closure time, you still have the possibility to change your nomination or your deals in some extent. In gas, it is possible until 2 hours for realization, in electricity until 15 minutes before. This is very important for consumption or production with strong fluctuation, for instance, for photovoltaic production. How does it work concrete? I'll try to explain with this chart how the forecast is made. What you see is the electricity production and the consumption in our balancing group at 3 days on last summer. On those days, we have a very small wind production. The production of our combined heat power units is quite stable, and we have a huge solar production at daylight, which is typical for summer. At the midday, we have even more production than consumption in our balancing groups. Before trading starts, we need to predict the demand for the following days and hours. So we extrapolate production and consumption with our forecast model. On the chart, you see the interrupted blue line is the forecast consumption, and the gray one is the forecasted production. And the difference is exactly the quantity you need to provide from the markets. In our case, the quantity is mainly covered by medium-term contracts in order to limit the price risk. And the residual quantities provide on the spot markets. We use short-term forecasts up to the following hour for that. If our balancing groups are short, we buy the residual quantity. If they are long, we sell it. In the first part of my presentation, I have explained you why you need forecasts to act as a balancing group and to provide customers with energy. Now, I will go with you our recipe to make forecasts as accurate as possible. Forecast is not divination. It is based on learning mathematical models. First, you need to identify the factors influencing energy consumption and production. You give this factor to the models so they can learn how they have correlated in the past and extrapolate it into the future. I took as an example here on the right side of the slide the gas consumption of a typical household in Berlin. Households mainly consume gas for heating today. Their consumption depends strong on the temperature. The gas consumption is represented here on the vertical axis, and the daily average temperature is on the horizontal axis. If you plot on the chart 365 daily gas consumptions, you get that quite pretty cloud of dots. It shows a very good correlation scheme. If consumption would depend exclusively on the temperature, all the dots would be on a single line. If the line was straight, it would be a linear correlation. In fact, the correlation is a bit more complicated. So you need more complex functions than a linear function. And you need to take some more factors into consideration if you want good forecasts. On the left side of the chart, I represented, or I listed all the influencing factors that we take into consideration in our models for gas and for electricity. The second important thing is to use the adequate models. As we have seen in the last slide, you cannot simulate the gas consumption of an household with a single linear function. You need models that are more elaborated. Actually, you need different models for different types of producer or customers. Which model you use also depends on the available data. It depends if you make short, medium, or long-term forecasts. It depends on the calculation capacity of your processors. And finally, it depends on the accuracy you need at the end. So on this slide, I listed the different models we use for the different types of consumers. Brain asked me to insist on this point. As we have already seen, as a balancing group manager, we have to deal with plenty of market players and with a huge amount of data. And in future, it will be even more data. So we need a high performance IT to do it. We have implementing software from different IT providers, which are represented on this slide. Each one supports specific business processes relevant for the forecast. In the middle of the slide, you see the energy data management system, which plays a central role. It deals with more than 2 million time series. Presently, we are implementing a new predicting core. It relies on a stronger artificial intelligence, and thus it will be able to automatically identify the best algorithms on the best models on the basis of the trained time series. And finally, I wish to insist on a point which is usually underestimated. For our forecast, we use data from very different sources. The quality of this data is very unequal. Every day, there are single market players which fail to deliver the data they should on time. Sometimes they deliver unrealistic measures. Data scientists say garbage in, garbage out. So you have to dispose the garbage first before you make your forecasts. Basically, we proceed in 3 steps. We track and patch systematic bugs. We replace unrealistic data, and we extrapolate the missing ones. As an example, I took on the right side of the slide one of our tools for data cleaning. It is a screenshot from the energy data management system, and it helps us to identify missing energy allocation so that we can immediately make a request at the DSOs. Let me finish my presentation with the most important advice in my eyes. Your data is the main ingredient of your forecast. So invest time and money to get good data. That is the unique way to get good results. So I thank you for your attention. I hope you enjoyed it. And I'm very happy if you have some questions.
Thanks a lot, Antoine. Yes, there were 2 questions popping up. So the first one is from Michel, and he's asking, is there any concrete change in the legislation already ongoing at the level of the German gas market due to this transition process. Does one of you want to give some more input concerning this? Nicolas or Antoine, or maybe both?
Antoine, it's your market, but I'm happy to jump in first if you want, and then you can add anything I'll miss, because I'm sure to miss a lot. What springs to mind directly in terms of technical evolutions, at least, is once again this overall discussion on the development of hydrogen and the way hydrogen should be dealt with in the grid. So in that particular discussion, as far as I'm aware, in Germany, there was a decision which allows for blending up to 10% in the grids. That in itself is a concrete change, because, of course, being allowed to blend in 10% also means you have to change a lot of how you do things. And particularly, you have to plan and make sure you have a good flow of information between your system and your end users. So in that respect, as far as I know, the Technical Association in Germany has also undergone a lot of work to test the whole northwestern area of Germany to see the extent to which blending and then converting large-scale systems, also with the reuse of L-gas networks that will no longer be used in the future, which could become the base for pure hydrogen networks. That is in the, let's say, overall next steps, which will have a concrete impact on end users and the way that DSOs and TSOs have to plan ahead on the way they manage their flows and on the way they ensure stable gas quality for end users in order to have a kind of security in the system. So that's maybe more of a high-level change, but I would say quite concrete. And again, Antoine, I suspect you have a lot more insight on the local aspects than I do.
I'm afraid I don't have so many, because, as you say, it's still a high-level discussion. The 10% limitation is actually the quantity that the gas network can take of hydrogen without changing so many things on the contractual level. And I'm aware of regulation on the contractual level between the low gas and the high gas quality. But at the time, we actually don't have the amount and quantity of hydrogen in the network that make obligatory to change the regulation to access to the network for a balancing group operator. So at the time, we don't have these rules, except for the gas quality high and low. But I'm sure it will come. That's really the point. Yes.
Okay, thank you. There is another question from Thomas for Antoine. What kind of forecasts? What tools do you use? Which methods do you prefer? I suggest you directly type in your answer under his question, because we have a couple of questions popping up now. There is a question from Michael, and I think it's for Antoine, and he wants to know, what is the volume-weighted day-ahead accuracy you achieve for gas demand forecasting? And he adds, feel free to disaggregate your answer for summertime and wintertime, and for non-daily metered consumers and all consumers. I'm not sure we will have the time to go into that much detail, but you can also type your answer directly under the question. And
that's what I would have proposed to you, because I didn't prepare so specific figures for the presentation.
Yeah, just
I can have a look at that and give them afterwards.
You can take your time and type in your answers directly in the question box. And there is another interesting question from Olivier. What kind of meteo forecast do you use? Are they in a grid for all Germany or for different points? And he imagines that every TSO, DSO should use the same forecast. What do you...
for us, it would be actually very good if all DSO would use the same forecast, but they are all free to use their own weather service provider. So we have chosen one on the market. Basically, I think they're set on the same framework of weather stations. More important for us is how we clustered all Germany, because we don't want to deal with a different weather station for each town or each city or each customer. So we clustered whole Germany in 12 regions, and we make our forecast on the basis of the weather data for these 12 regions. Of course, it's not so accurate as it would be if we had a weather station sitting near to each customer, but it wouldn't be possible to handle so much data. So we made a compromise, which is this 12 station.
Great, thanks. And then there's another question, and then we will hop on to Maël. A question from Marc. Can you give examples of precision of your provisions? So my guess would be that the more precise your provision is, the better for everyone. How precise can your provisions be?
You can't answer this question with one figure, because the precision you have for household customers is very good. It is much worse for a photovoltaic producer, because and it depends on the time you have. The weather forecasts will be more accurate if you make it 1 hour before, so you can take into account if there are some clouds in the skies and the production of photovoltaic is reduced because of that. And for the electricity market, it is important to have this short-term provision on forecasts. For the gas market for household in Germany, well, you have to take into account the temperature of the day on a few days before until 4 days before. So you get some better accuracy.
Okay, thank you, Antoine. There is one last question for you, but once again, we're running out of time, unfortunately. So I will let you answer on the right-hand side in the questions tab. You can answer directly. And now we will head over to Maël, who's a data scientist at DC Brain. And Maël, I'll just let you take it from here. Thank you.
Thanks. Hello, everyone. Thank you to Nicolas and Antoine for the presentation. It was very interesting. Nicolas for the big picture and what will come next, and Antoine for the more technical view and especially on the forecast. It was a very good presentation. So I think, Nathalie, I have my slide just after. Okay, that's good. So on my part, I will mainly present 2 use cases. So it will very practical. It's 2 things we do at DC Brain on the gas sector. So the presentation will be divided in 3. First, I will try to show to present an overview of the gas energy sector. As Antoine said, it can be complicated, so I do my best to do a simple overview of how it works, and then I present first a forecasting conception project that we have, and second, a gas quality one. So let's go for the overview. I'm not as proud as Antoine on this slide, but I did my best. So we can see that there is three main actors: the suppliers, the transport, and the distributors. First, we will focus on the physical network. So what the gas flows from where to where, because it's the simpler thing. So it goes from producer, then transport. So the transport is kind of the highway for the gas. So it's like big pipes and high pressure. Then there is the distributors, and the distributors carry the gas from the transport to the end consumer, so you and me. And then, so you and me, we don't care about all this. We just subscribe to one supplier, and the supplier do his best so that the contract is done in gas. And so what does he do? He have to ask to the transport to carry gas, and then the distributor carry it to the end consumer. So each actors have their own challenge. For example, the supplier, what is important is to make a good forecast, because he's the one who will ask in volumes of gas to the transport to carry on to the end user. The transport, the challenges are more a challenge to how to store the gas, how to balance big networks, how to maintain good quality at each exit point. And the distributors, it will be also gas quality. You have to ensure that each client have proper gas quality for them, and also consumption forecast, because he's the one who check on all the pipes that go directly to the end users, and he's the one who read on the index of each clients to know how much they consume. So I separate these different challenge for each of the actors, but actually it's overlapping. So there is forecast is important for supplier or for distributors, and gas quality for distributor and transport. But so this is the I think a good overview of how it's going on. So next, I will go on to the first use case, which is consumption forecast. So why it is important for the distributor and the supplier to have a good consumption forecast? It's essentially because what they ask, what is asked in terms of volume every day of gas, it's a clear number. They have to tell it to the transport. But on the other side, we don't measure every day what is consumed. For most of the end consumer, it's once every 3 months, something like that. And so it's difficult to adjust between what is allocated and what is actually consumed by the end consumer. So as I said, every day the supplier asks for allocations to the transport, and each month there is some regularization that is done between what was allocated and what was really consumed. So at the end, someone has to pay the difference if we allocate too much of or not enough. So that's why this is important to have a good forecast on the consumption. So what data do we have to do this good forecast? I took, the use case that I talk about is about one distributor. So typically it's a city gas network. Here there is one entry point. It's to simplify the thing, but it can be a lot of entry points. So what do we know in terms of data is that every day we know what enters the networks in terms of volume of gas, but we don't know what each individual clients have consumed. And the problem is that the distributor have to tell to each of the suppliers how much of these volumes comes from their clients. So to do this, we have to make good models of all the individual clients. And so there is some clients with daily meter to know what they consume daily, but it's really few of the clients, and most of the clients are read once every 3 months. So today, what distributors usually do is that they use profiles, and so the profile is based on the client profile. So if it's a big consumer, a little consumer, and there is also a base consumption value that is computed from historical data. But usually these profile and values are updated only once a year. So it can be a problem because the behavior of the end consumer may change during 1 year. And also, as it was not by Antoine, the consumption depends on multiple factors, but it depends a lot on temperature, and as it can, some months can be like colder or hotter than the previous years. It's important to have a dynamical model that can be adjusted through the year. Another difficulty that arise, it's not only that you have to make a good model of prediction of consumption, is that you have to make individual models, and there can be on the network that can be that 100,000 to 1 million clients. So it's hard to, I mean, it's a difficulty to make so much models at the same time. And the second thing is to have model that can refine dynamically if there is a lower temperature or if the client change of behavior. So here's an example of a project we just done. So it was for the month of January 2001. So I just put the sum of all the prediction we made, and so it's 95 daily accuracy. So it's pretty good. So that's the end for the consumption forecast part. Now, so it's completely other subject. So it's gas quality. It's always on the distributor part. So what is done here is that the distributor have to is comply to give to the end user an amount of what we call HCV, so it's higher calorific value. It's just mean a certain amount of energy carried by the gas. So the distributor has to give to the end user a specific HCV value. The problem is until now, when there was not mixing of different gas, this value was just the value that was put at the entering of the network. So there was not so much to compute. But now that there is different gases like biomethane or hydrogen with very different HCV value, the distributor has to compute this mix through the network because the gas mix, so the value of the HCV will be very different from one point to another on the network. So again, what data do we have? On this part is more what data do we need? So let's take a network, so like a city gas network. We have multiple entry points. Each of the points have different HCV, so they carry different amount of energy, and we have to know for each end consumer which is the mix, so the value of the HCV. So what do we need is the topology of the network, so that we can make a physical model and compute each of the HCV points. So how does it work? The first thing, as I said, is we take the topology of the network. We build a digital twin. It means that we will make a physical model on our network model. Then we can compute all the flow through all the pipes of the networks. And once we have all these flows, once we know how the gas go through the pipes, it's really easy to compute this HCV value. And then we can compute it for each end user of the network. It might be my last slide. No, yes. So on this point, there are already software that exists, but the problem is that usually it's really hard to set up this software when there is missing data, which is always the case when we work in industrial with industrial groups. So it's kind of difficult to put it in place. So what is good with our solution is that it's really flexible. It's easy and fast to instantiate, and it's fast to compute. And as there is a lot of missing data, we can easily fill the missing data. So at the end, we have good result. And I think that it was my last slide. So thank you. If you have any question.
Thanks a lot, Maël. There have been a couple of questions indeed. I suggest you just get back to the questions and take some time to answer them just by typing the answers in directly. And this way we will have the opportunity to listen to Arnaud. Arnaud de Moissac, who's the CEO of DC Brain, and who will take care of the conclusion of this meetup. And thanks again to everyone who attended. And Arnaud, you can take it away. Thank you.
Okay, do you hear me? Okay. Well, first, thanks, Nicolas, Antoine, and Maëlle, of course, and Nathalie. It was really, really interesting. Perhaps to summarize in few words, Nicolas told us about the big picture, about the fact that we need optimization, we need data, and we need forecast. And the interesting part, one of the interesting part was that it's not about innovation or about R&D. It's really about the new gas grid reality. It's not about the future. It's really about the present and one we need to put in place to be able to continue to have a good gas grid operation. Then Antoine gets deeper in the forecast needs and the value for the network. And once again, the topic was not about how you can forecast time series. It was about how can you really expect to operate your gas grid without forecast, and without regarding the complexity of the market. Without the forecast regarding the complexity of the market and the number of constraints, and of course, a small conclusion, but very, very important, about the data quality and about data management. And finally, Maëlle reminds us that even if you are able to train a good model, it won't be really useful unless you are able to train thousands of different models, including gas links between the models. And well, for someone who is not a data scientist, who data and forecasting is not his everyday job, it can be quite scary, by the way. Because when you are able to deal with gas grid, compressor, distribution, transportation, it's really a tough job, and you don't have, well, it's not your knowledge field to know how to train models and deploy models and do that in an industrial way. So we need data management, we need forecast, we need optimization. And even if it's not in the DNA of gas grid operator, we just seen that it's no more a problem, because there's already industrial ready-to-use solution dedicated to gas, like DC Brain, and those solutions are existing today. They are working. They are easy to deploy at an industrial grade. Well, so you just have to jump in. Thank you.
Okay, thanks a lot, everyone. Well, there are a couple of questions that haven't been answered. I will try to integrate them into the recap email that everyone will receive tomorrow, so no one leaves this place empty-handed. Thanks a lot again, Antoine, Nicolas, Maëlle, and Arnaud, and we hope to see you soon for another meetup online. Thanks a lot. Goodbye, everyone.
Thanks for the invite.
It was a pleasure.
Great. Thank you. See you soon.